Hello, now we have in the sequence of the counter, we have another counter that is called as Johnson counter, and it has another name, twisted ring counter, or it is also called as Swiss tail ring counter, and it is one of the example of the synchronous counter, and we know that why it is called as the synchronous counter since same clock pulse is given to the all flip-flops. So all flip-flops can be triggered at the same time. So again here we are going to use the uh, concept of the shift registers. So from each stage we can have output here A, B, C, and last one is what here E. So why it is called as switch tail means in case of ring counter, if you can recall, there was the feedback from the output E, but here we have feedback from the E dash. So last tail is connected back to the first flip flop. So that's it is also known as switch tail ring counter, or many times it is also being asked with the help of by the name twisted ring counters. So now in this, since it is constructed with the help of D flip-flops, so whatever input is going to occur here, same output will occur at the output. And whenever E will be 0, E dash is going to be 1. And whenever E is 1, E dash is going to be the 0. So on the basis of that, if you see that when initially we have E0, so the input to the flip-flop, first flip-flop is going to be 1. If whenever E is 1, then input to the flip-flop, first flip-flop is going to be the 0, since it is connected with the Q bar here. So that things we have to keep in the mind before understanding the operation of this. Now in the initial stage, for the zeroth clock, we are considering that A, B, C, E, all outputs are 0, 0. So here is the binary equivalent in decimal is 0, so used states is 0. Now since E bar is connected back to the D, so that E bar will become 1. So that is going to appear as the output. So A is 1. And finally, here shifting will takes place. So this 0 will come here, and this 0 is going to come here, and this 0 is going to come here. So finally, you are seeing that again equivalent of this is 8. So number of user states is here how many? 8. In the next stage, again what we are going to observe, again E is 0. So E bar will become 1. That is going to be the input here to the first flip-flop. So A is going to become 1 again. And this 1 is transferred here. Again, this 0 is transferred here. And this 0 is shifted here. So its equivalent is now how much? 8 plus 4, 12. So here now we'll see that used states are 12. Again, E is 0. Is still what we have? E as the 0. So E bar will become 1. That is the input here to the first flip-flop. So A is going to become here 1. What is the E bar? Same thing is going to appear here. And this 1 is shifted here, A to B. Again, this is shifted B to C. Again, this is shifted from C to E. So finally, if you see the equivalent, 8 plus 4 plus 2, 14. Again, if you see that still we have E as the 0. So this 0 means E bar is 1. So again it is given back. So A is going to be the E bar, that is the 1. And again it is shifted here, A to B, B to C, C to E. So now all A, B, C, E are become 1. So that equivalent is how much? 15. Now finally what we are seeing, observing here that E become 1. So E bar will become 0. So that's why now here earlier what we have seen that here input was becoming 1 always. Now here input is going to be 0 now to the D flip-flop. So that's why A is also going to become 0. Earlier A was what here? Going to be 1. So now E bar is 0, so A is 0, and this is shifted here 1, A to B, again B to C, again C to E. So now its equivalent is what? 7. So again, if you see that Now here onwards, what you are observing that E is again 1. So E bar is 0. So A is 0. So further it is shifted here A to B, B to C, and C to E. So its equivalent is what? 3. So used states are 3. Now again E is 1. So E bar is 0. So A is going to be 0 and it is shifted A to B, B to C, and C to E. So finally what we have again 0 0 0 1. Its use state is what? 1. And at last we are going to observe here that again E is 1. So E bar will become 0. So finally A is what? 0. And all is going to shift in the same way A to B, B to C, C to E. So again its equivalent is 0. So finally if you'll observe that this first state and this last one is both are same. So here after repetition takes place. So here total 8 unique states we have here. In case of Johnson counter, 8 unique states we are getting when we have 4 bits, or we can say that when we have 4 flip-flops. That means if you have n bits here, so then we'll get 2n unique states. And in this case, for this given example here, we have 8 unique states. So with the help of 4 bits, we have total combination is to the power 4 is what? 16 combinations are possible. Out of that, 8 are used states. So here for this given example, number of unused states become how much? 16 minus 8, that is the 8. So in general, we'll have 2n unique states in general for n number of the bits. So in that case, we'll have number of unused states in case of Johnson counter is to the power n overall minus 2n. So that is here advantage in case of Johnson counter, and it can be designed for any bit of sequence. So here we have total 8 unique states in case of 4 bits. So number of states is going to be the twice, that is the 2n here, and number of unused states are being reduced, that is the to the power n overall minus 2n. Thank you.